Good evening, everyone. One, two, three. We are 6 at the moment. We'll give them 1 minute to see if someone else joins, and then we can start. Yep. So you can all hear me, see the screen? Okay, perfect. So I received one question. We'll first answer that one, and then we can see if there are any others. So the question I had, or that I received, was on the river example. So normally you should see the screen of the river example with the quality of the estimation. And then there was the Fisher information matrix calculated. If you invert this, you get your error covariance matrix. So this one. And then the question was from here, how do we go to the confidence intervals and the parameter correlation? And so I copied the formulas that we need. So you have these on page 80 and 81 in chapter 10. So if you look at the slides there, you will find the formula for the correlation as being the covariance divided by the standard deviations. And then also the formula for the confidence interval. So theoretically, these are those two. For the correlation, which is easiest, what you do is you take the covariance. So that's the, so to calculate this one, what you need is the covariance between both of them divided by each of the standard deviations, so by the root of the variances. And these you simply find in your correlation or your covariance matrix. So the covariance is off diagonal, so it's a 2.96 times 10 to the power minus 6. And then the other two, they are on the diagonal, so it's a 2.12 10 to the power minus 5 times 2.52 10 to the power minus 6, and then you take the root of this. This gives you a correlation of 0.41, and I'll also show the calculations specifically later on. And then for the confidence intervals, you have to use the formula with t quantiles. The additional information that you need for this, and which is not given in the slides I saw, is that there are 25 observations, and we are looking at so that one you had PS2 because you have a 2x2 covariance matrix, so you have two parameters which you are considering, K1 and K2. So this gives me a t quantile for a distribution with 23 degrees of freedom, and then we needed the 97.5 quantile because we have a two-sided interval. And then this is just again what you find here on the diagonal of the covariance matrix. So let's see if I now can share the other screen. So normally you should now see R. No, this is in the way. So I here already coded the things. So C, as you can see, is just the covariance matrix that you had on the slides. For the correlation, what you do is you take the off-diagonal element, so the 1, 2 element, which is the covariance, and then you divide by the root of the variances. So if you do this, you see that the correlation is 0.4049. So if you round it, you go to 0.41 or 0.40, depending on how you do the rounding. So this was also what's in the slides. Then N25 observations, P is 2 for the degrees of, well, for the number of parameters that we are considering. So we have 23 degrees of freedom. And then the quantile that you find in the T distribution is 2.068658. Or if you take your course notes at the end, you also have the tables. If you look it up in your tables, you will find, I think, 2.069. I think they give 3 decimals, but it's not a big difference. And then you can calculate the size of the confidence interval. So I just calculated the size of the confidence interval. So it is TT, so the quantile that I just found in my T distribution, times the standard deviation from the covariance matrix. So TT times the root of the first diagonal element for the first confidence interval, and TT times the root of the second diagonal element for the second confidence interval. And then if we make these calculations, we see that the width of the first confidence interval is indeed, so it's the plus minus 0.0095, as was in the slides. And then for the second, it's 0032 or 0033 if you do the rounding correctly, which also corresponds to what was in the slides. Bang. Does this answer the question? If I find my chat part back. Good, perfect. You're welcome. Now we go back. You did see my R screen, right? Because I was given it, but I'm not sure, because if I share screens, everything switches over here. So okay, good. Are there any other questions then? Chapter 10, page 74. Okay, let's see. With the simplex. No. It's always one of the actions at a time. The simplex algorithm is very difficult to understand, I know. I saw it as a student as well. It was one of the hardest things in the course. The basic idea is that you can only do these 4 actions one by one. And then let's see why 7 and 8. 1, 2, 3, Yeah, so you have in the previous step, so this is 4, 5, 6. What you see here is that the fifth one is the one which is most away from the center, so which will have the highest value. So what happens is you take a reflection there to 7. So in the next step you will have, you will have points 4, 0.6 and 0.7, which are left over. And then again, in this step, what you see is that point number 7 is the one which has the highest value for your function, because this one is outside of the, well, it's not really an ellipse which is drawn, but this one has the highest value. No, sorry, you're right. Apparently the reflection is taken with 4, so it's indeed a bit strange. Yeah, I understand your confusion now. Yes. So it's indeed done as if 4 would have been reflected to 8, but it's not logical because 7 seems to have the highest value. So you are probably right that there is something strange going on. But since I just copied this picture, I don't have the details of it. But so normally you would indeed expect that 4 and 6 remain, but 7 goes away. But for the simplex, it's well, I will never ask you to explain the simplex. If you can apply it with R or so, that's fine. But indeed, thank you for pointing that one out. So page 71. Good. And the other one? So is the length of the ellipse confidence interval for parameter. So OED, yeah, not really. So you don't really. So the question is the length of the ellipse the confidence interval for the parameter? Not really as such, because the ellipse is a confidence region in 2 dimensions. So this is the ellipse which contains 95% of the plausible values, but in 2 dimensions. If you look at it in 1 dimension, you get indeed a confidence interval in the directions of the axis. But they are, wait, are they the same for the single ones? No. No, so this is 95% confidence region. For your parameters, so this is your coupled theta1 hat, theta2 hat. But this means that my theta1 is here. And so my confidence interval, if I look in one direction, will be something which is symmetrical here. So it will never be the same as the length of the ellipse. So it's not because you have this length in 2 dimensions that it corresponds to the projection on the x-axis or so. So this is really a confidence interval for the 2 dimensions at the same time, but you cannot say that the length of one direction is the confidence interval for one of the parameters considered as a univariate variable. So there you will have to use the basic calculation again. Any other questions? So I'm going to copy it again to everyone. So in the autocorrelation test, why should the normalized covariance remain within certain confidence bands? Because you saw in one of the previous chapters that this normalized covariance follows a standard normal distribution. So the confidence band basically corresponds to a confidence interval if you look at each of the time points separately. Something like that. Where was it? Was so here basically what you do, you look at the autocorrelations. Then we've seen that the autocorrelations, well, so this is a bit easier. So the autocorrelations you see, you have to compare them with the standard normal distribution divided by the root of n. So it is a normal distribution over root n. And so basically what you are doing is just checking that each of the autocorrelations, each of these values separately, is a plausible value, yes or no. Okay, wait. I'll first. And so what you want to do is just the same as in another test, is to see that in the end, these values, they remain within your confidence band. And so the reason for this is just that you have, or you can prove, I think I did it in one of the previous Q&A sessions, so you can check that one online, that this is a normal distribution. And so these values, you just get them from a normal distribution. So you get the confidence band for the normal distributions, and then you check that the autocorrelations stay within to make sure that they converge, or that they, at least that they stay small enough to be plausible values. Modeling simulation, data. So modeling and simulation is indeed a bit harder in the sense that it's, yeah, it's a thing that has been added to this course. So before you had a course on modeling and simulation itself, which contained a part on modeling, which was given by Professor Rao, and then a part on simulation afterwards, which is given by me. The modeling part is now gone to modeling and control, I think the course name is. And then the simulation part had to go somewhere, so it's added to this course. I think it was perhaps more logical to keep them together in the same course. But yeah, that's also the reason why there is no written course material except for the slides for this part. And the idea is indeed a bit different. It's also, well, it's more important for this part to be able to apply it and to know that there are different techniques to find the optimal values, to see how you can calculate the quality of the estimation, sensitivity analysis and such. So here, how deeply do we have to understand it to solve the problem? You have to understand the basics of it. So you have to know, for example, what a sensitivity function is, what it does, but not all the mathematics behind. So for the final part, it's the most important thing is to understand it, in a sense that you know why we do these things, in general how they are done, but not every single detail. So you need to know the difference between, for example, random sampling and then the Latin hypercube sampling. You need to know, for example, what Monte Carlo is, sensitivity functions, so the difference between a relative and a global sensitivity. But the general ideas, the concepts, and not all the little details. Whereas for statistics, there you have to understand why you are doing it, but also for testing, for example, how you do the testing step by step. You're welcome. Are there any further questions? If there are not, we can conclude this Q&A probably. Anyways, if there are other questions coming up later on, you can always send me an email. I'll try to reply to them through mail. If there are problems or there's something that you don't understand, just let me know. And then, yeah, for the rest, I already, well, I won't see you again, most likely. So good luck with studying already, and then good luck with the exam. And then, yeah, I hope not to see you again in August, but that's still a long way. So anyway, if there are problems, if there are questions, just send me an email and then we will see how we can solve them.